Today we're solving LeetCode 3453, separate squares I. This problem looks geometric, but the real test is whether you can convert geometry into math and binary search, which is a very common interview pattern. By the end of this video, you'll know exactly how to balance areas using a horizontal cut, even when squares overlap. We're given several axis-aligned squares on a 2D plane. Each square is described by here, x, y represents the bottom left corner, and L represents the side length. Our goal is to find the minimum y-coordinate of a horizontal line such that total area of all squares above the line equal to total area of all squares below the line. Important details. Squares can overlap. Overlapping area is counted multiple times. Answers within 1 times 10 to the power of -5 are acceptable. So this is not about union area. Each square contributes independently. Example 1. The input is a list containing 2 entries, 0, 0, 1, and 2, 2, 1. We have square A spans from y equals 0 to y equals 1. Square B spans from y equals 2 to y equals 3. If we draw a horizontal line at y equals 1, square A lies entirely below the line, so its area is 1. Square B lies entirely above the line, so its area is also 1. Balanced. Any y between 1 and 2 works, but we want the minimum, so answer is 1.0. Example 2. The input consists of 2 squares, 0, 0 with side length 2, and 1, 1 with side length 1. Here squares partially cross the line. At y equals 7/6, which is approximately 1.16667, each square is split by the line. Part of each square lies above the line, and part lies below it. When we sum all the partial areas, the area above the line is 2.5, and the area below the line is also 2.5. This shows that we are splitting squares, not selecting entire squares. This is not a geometry sweep problem. Instead, think of the horizontal line as a variable y equals mid. For each square, we compute how much area lies below the line and how much area lies above the line. Then we add these areas across all squares. As y increases, area below monotonically increases. Area above monotonically decreases. That monotonic behavior immediately suggests binary search on the y-coordinate. Why brute force fails here? A naive approach would be, try many y values, recompute areas each time, but coordinates go up to 1 times 10 to the power of 9. Precision required is 1 times 10 to the power of -5. Trying every possible cut is infeasible. We need something logarithmic. Step 1. Define a helper function. For a given horizontal line y equals mid, we process each square one by one. For a square, the bottom edge is at yi, and the top edge is at yi plus li. There are 3 possible cases. First, if the square lies entirely below the line, its full area contributes to the area below. Second, if the square lies entirely above the line, its full area contributes to the area above. Third, if the line cuts through the square, we split it. The height below the line is mid minus yi, and the height above the line is yi plus li minus mid. The area contributed in each part is the height multiplied by the side length. Step 2. Binary search. We perform a search over the vertical range. The lower bound is the minimum yi among all squares, and the upper bound is the maximum of yi plus li. At each step, we take the midpoint y equals mid. If the total area below the line is less than the total area above the line, we move the line upward. Otherwise, we move the line downward. We repeat this process until the precision is good enough. We define a class called solution. Inside it, we define a function named separate squares, which takes a list of squares as input. First, we determine the vertical search range. We set low to the minimum y-coordinate among all squares, and high to the maximum value of y plus the side length. Next, we define a helper function called area difference, which takes a horizontal line y equals mid. Inside this function, we initialize 2 variables, below and above, both starting at 0. We then iterate through each square. For a square, the bottom edge is at y, and the top edge is at y plus l. If the line lies completely below the square, the entire square contributes to the area above. If the line lies completely above the square, the entire square contributes to the area below. Otherwise, the line cuts through the square. In that case, the area below is mid minus bottom multiplied by the side length, and the area above is top minus mid multiplied by the side length. After processing all squares, we return the difference between the area below and the area above. Now we perform a binary search. We repeat this process 60 times, which is enough to guarantee the required precision. At each step, we compute the midpoint. If the area below is smaller than the area above, we move the lower bound up. Otherwise, we move the upper bound down. After the search converges, we return the final value of low as the answer. Time and space complexity. Time, O of n log r, where r is the coordinate range. Space, O of 1 extra space. Efficient enough for 50,000 squares. Common mistakes and edge cases. Trying to merge overlapping squares. Not required, overlaps count multiple times. Binary searching integers. This is a floating point answer. Stopping too early. Use enough iterations, almost equals 60, for precision. Using union area logic. This problem is about summed contributions. What we did, converted geometry into a 1D area balance problem. Observed monotonic behavior. Applied binary search on the answer. Interview tip. When a problem asks for a minimum value that balances something, always ask yourself, is this function monotonic? If yes, binary search is usually the correct move. Thanks for watching. See you in the next problem.